For those who are joining and still don't know who Dr. Senecal is, he's the co-founder and owner of the Convergent Science company and one of the original developers of the CONVERGE, which is an industry-leading CFD software. Also, he works at the University of Madison, Wisconsin as an adjunct professor. Before Dr. Senecal starts with his presentation, I would like to encourage you to post your questions through the presentation on the chat that we have available on Teams. And these will be collected by Luca, also another member of the CFD Society, and he will proceed to ask them to Dr. Senecal after the presentation has been finished. Now, without further ado, I will leave Dr. Senecal to start with the presentation on CFD feature propulsion system design. Thank you, Dr. Senecal. Now you can start sharing your screen, and we will be all muted.
Okay, I do just want to make sure people can see my screen though, and also hear me. If someone could confirm that.
I can confirm that your screen is available for everyone, and also I can hear you clearly.
Perfect. Okay, well, thank you for that nice introduction. And as you already heard, the title of my talk is CFD for Future Propulsion System Design. And I want to give some acknowledgements before I start really getting into the presentation this morning. Well, this morning for me. So for me, I'm in Madison, Wisconsin. It's 8 a.m. here. I realize for most of you, I think it's 2 o'clock in the afternoon. So again, thank you for coming. And I really want to thank the ISCFD team for inviting me. As you heard before, this was originally supposed to be an in-person presentation. And I do hope that I can visit the university there in the future and give an in-person presentation, but we're doing the best we can right now. So this virtual method, I think, is almost as good, maybe. At least we're going to go with that. So I do also want to acknowledge, a lot of the work you're going to see in this presentation. We have a really great team here at Convergent Science. We are a global team, as I'll talk about in a few minutes here. And, a lot of the work you're going to see and a lot of the developments you're going to see in this presentation wasn't done by me, but by many of the members of the Convergent Science team. And I do also want to acknowledge our collaborators. So we work a lot with national laboratories, universities, and other research institutions. You'll see a little bit of that in this presentation as well. And of course, our clients, our customers, the people who buy our software. They motivate us to continue to innovate. So you'll see a little bit of that as well in this presentation. Okay, so here's a quick outline of what I'll be talking about today. I'm going to first start out with some background. I'll talk a little bit about our company and about our software, just for those of you who aren't familiar with it. I will talk about CFD for propulsion system design, of course. That's the main topic here. But I also want to talk about what is the future? What is the future for propulsion systems? And how does CFD, what are the core features of CFD that will help carry us into the future? Because, of course, as CFD folks, we want to use CFD as much as possible to help design whatever we're working on. In my case, it tends to focus on propulsion systems. And so how will CFD help us? And then we'll conclude it at the end. Okay, so as you heard already, I am one of the co-founders and co-owners of Convergent Science. We started developing Converge quite a while ago. We started developing it in 2001 is when we wrote our first line of code. And what we were really trying to do was address CFD bottlenecks. So we were doing engine simulations using a code called Kiva. Some of you may be familiar with Kiva. It's a US national lab code out of Los Alamos originally, but it's been modified and improved by a lot of places, including the University of Wisconsin-Madison, where we went to graduate school. So Kiva was a great tool and a really nice tool to learn CFD on. But one of the downsides with Kiva and many CFD codes, especially back then, was it took a really long time to generate the mesh for what you're trying to simulate. And especially with engines, as we'll talk about, in a few slides here. It's a very complicated problem. So we wanted to write a new code that would kind of remove that bottleneck. And so users of CFD could just get right down to doing the CFD and not spending, we had people in graduate school there spending weeks, months, sometimes even like a year or so just creating a mesh. It was that crazy and that difficult. Then in 2008, so we'd been developing our code for about 7 years and doing consulting and things like that as well in our company. And then in 2008, we were ready to go commercial with Converge. So all of our growth has really been since 2008. In 2008, we had 5 people, and we have about 150 employees worldwide right now. And most of the major auto and engine companies are using our software. So here's a map showing kind of where we're located. So hopefully you can see my cursor here, or my pointer. And our headquarters is in Madison, Wisconsin. So we are a couple of hours north of Chicago. So if any of you have been to Chicago, or maybe you've been to Madison, certainly if you ever come in the future, you're welcome to visit our offices, but we're in Madison, Wisconsin. We also have a small office in New Braunfels, which is in Texas. And that's very close to Austin, Texas. It's kind of between Austin, Texas and San Antonio, Texas, if you've ever been to Texas. So we have a small office there. And then we also have a small office in Detroit. As you can imagine, we have a number of clients in the Detroit area. And so we have a small office there to kind of help serve those clients. And then as far as Europe goes, our main office in Europe is in Linz, Austria. So we have a number of people there. And then we also have an office in Pune, India. And that we started just a few years ago, and that's grown quite a bit and continues to grow. So all of these offices in yellow are our Convergent Science offices. But then in Asia, in Japan, Korea, and China, we have a distributor called IDAJ. And many years ago, they were called CDAJ. And maybe some of you are familiar with that. They used to be CD Adapco's distributor many years ago. But for several years now, they've been our distributor, and they've since changed their name to IDAJ. So they handle all of our Japanese, Chinese, and Korean clients. Okay, so that just gives, and here's a picture of our headquarters. This is where I'm sitting right now. My office window is, I'm kind of right down here. You can see my cursor. So that's our office, and that's where we probably have about 85 people here in Madison, and then the rest of the 150 are kind of in those other offices. So that's just a quick rundown of kind of our company. And I do want to start off with some non-propulsion system simulations, because I want to kind of make the point that Converge, although we do a lot in the reacting flows and propulsion systems and things like that, we are a general CFD code. And where we really shine is for problems that have complicated geometries with moving boundaries. And the reason for that we'll get into in a few moments, but I just want to show a few kind of quick simulations from very different areas, right? This is a wind turbine farm. And I don't know how well it's coming through the internet, but the blades are rotating. We even have a truck kind of driving down the road here. And we have kind of a complicated terrain. So problems like this, again, because of the way we wrote Converge, are very easy to get started in Converge, because the mesh is completely automatic. Okay. Here's another case, and this was done in collaboration, or not done in collaboration. Argonne National Laboratory did this on their own, but they used our software to do it. And I actually, I have some more videos that I wish I would have included in my presentation, but if you go to our YouTube channel, you can see those. But they're starting to look at quadcopter simulations with Converge. So this is just looking at one of the propellers. And then here we're looking at vorticity on a cut plane. Let me play that again. And again, this is obviously has rotating boundaries. Again, this is very easy to do with Converge. We also do a lot in the fluid structure interaction area. And again, the reason why we do really well in this area, again, is because of the way the mesh is automatically created. I don't know if you can see these rods, but hopefully you can see them vibrating, and that's reacting to the flow, right? So that's not prescribed motion. that's actually reacting to the flow via fluid structure interaction. So there are a lot of applications where, you know, being able to do this very easily come in handy. Maybe some of you are familiar with those. And then here's a little more of a complicated simulation, but this is again using FSI. Here we're doing a rocket launch. So again, we're not prescribing the motion of the rocket. It's calculated through the fluid structure interaction. We also do quite a bit with volume of fluid, so multi-phase flows, and we'll talk about that in the context of propulsion systems later on. But this is a paddle wheel. So this is a paddle wheel on the back of a boat, and you can see we have water and we have air above it, obviously. So we're tracking the interface using a volume of fluid method. Let's just watch this for a minute. Now you can see the mesh, and you can see the adaptive mesh refinement, which I'll go into more detail on in a few minutes. Okay, but a lot of what we do is reacting flows, and here's just another sample case. This is a HiFire 2 supersonic combustion ramjet. On the top, you're looking at an isosurface of the stoichiometric mixture fraction. On the bottom, you're looking at an isosurface of the Q criterion, which is colored by velocity magnitude. Oh, sorry about that. Sorry about all the branding on this one. But there you can see, you can visualize the vortices there. So again, we do a lot of these types of applications. And we also do quite a bit in the gas turbine world. So for jet engines, I'm not really going to focus on that in this talk. I could do a whole presentation on that, but I just wanted to give you a little bit of a flavor there. And one of the things that is a real problem with gas turbine is this relight problem. And if some of you may be very familiar with this, but you have a fuel-air ratio mismatch during a flight, right? So that can lead to flame out in a gas turbine engine. That's pretty scary. So it occurs 1 out of every 100,000 flights. So about once per day. Well, right now it's probably not occurring very much at all because not many people are flying, but in general, you know, about once per day when we have sort of normal situations. So it's not a lot, but I don't want to be on that flight where it's happening the once per day. So these engine manufacturers need to be able to come up with a reliable relight within a certain amount of time. And that can be a great challenge, right? And so traditionally this was done experimentally, but what we've been working with some manufacturers and they've been finding that actually using our software, they can predict this relight, right? So we have to be able to test the engine in altitude conditions to establish these relight characteristics. And this test case we're going to look at is a University of Cincinnati 5 swirler array. We have the swirler here, we have the spark igniter. So let's look at that in a little more detail. So here's an animation on the left showing the 5 different swirlers and then showing how you initially spark the first one and then that spreads and ignites all of the other ones. And then really that's the challenge, and that's what we're trying to do. And if we look at this versus experiments, these are experimental images right across those 5 swirlers. And then if we look at our simulation results with an isosurface, you can see that qualitatively it looks very similar, right? So we're able to capture the amount of time it takes to ignite across all 5 burners, as you can see in these images. Now, if we go a little further with that, we want to be able to do simulations where we change the spacing between the burners, for example, and still predict the propagation time as a function of fuel flow rate. So here you can see experimental data for a couple different conditions. One is 2 diameters apart, the spacing between the burners, and the other one is 2.5 diameters apart. And you can see the sensitivity of that in the experimental data with the symbols, with the black symbols. And then if you look at the blue triangles and the red squares, you can see we actually capture quantitatively that propagation time really well. So this is kind of an exciting area for us and a place where we can really help sort of the gas turbine industry design their engines for relight. Okay, so now let's go into sort of more of the automotive side of things, right? That's kind of the core of what we're talking about today. CFD for propulsion system design. This is showing an animation of an engine. And the point of this simulation is just to kind of show all of the complicated features that an internal combustion engine simulation has, right? So first of all, you can see that replays, no? Okay. First of all, you can see that some of the geometries are fairly complicated. You have the spark plug. You can see here, different length scales for sure. You have moving boundaries, the piston moving up and down, the valves moving up and down. Then you have multi-phase flow. So you have in this case, this is a port fuel injected engine. And you can see the liquid, every once in a while, you can see the liquid injecting. Let me play it again. Thought I had this on repeat. So if you look closely here, you can see the liquid injecting. That has to mix and that has to go into the cylinder, has to further mix. So complicated turbulent flow, multi-phase flow, chemically reacting, because eventually we spark the mixture, and then we have combustion, and then also heat transfer. So here we're doing a conjugate heat transfer simulation. So we're actually coupling the fluid flow with the solid and predicting sort of the solid temperatures as well as what's happening inside the cylinder. So this is what really got me excited back in graduate school about engine simulations, because really I was a CFD person and I wanted to do a very challenging CFD problem. And this was one of the more challenging problems out there. So this is what got me into doing engine simulations. Okay, and if you look at sort of the opportunity here, I don't expect you to look at all of these tables, and some of them aren't even labeled, it's just for show. There are lots of variables in an engine. So a lot of people will say, well, we've kind of reached peak with engines. We can get much more out of them. We've gotten the maximum efficiency. We've made them as good as we possibly can. And I say, no, that's not true. There's a lot of design space here that we haven't explored yet. And what better way to do that than with CFD? And so that's kind of the topic of today. And a really good example of that is this engine made by Mazda called the Skyactiv X. And I include this one because I think a lot of people have heard of this engine. We first started hearing about this engine maybe a couple of years ago, and Mazda made a breakthrough, and they were able to increase the efficiency by 20 to 30% using this new engine. And really, I'm not going to get into the details of exactly how this engine works, just because I don't have time, but they use something called spark plug controlled compression ignition. And really what it does at the end of the day is it combines the benefits of both gasoline engines and diesel engines, right? So, diesel engines tend to be more efficient. Gasoline engines have more power and things like that. So you combine the benefits of both and you have the Skyactiv X engine. And how did they do this? How did they come up with this new engine? Now there's a lot of words here, but I do want to read some of this because I think it's important. And this is an interview with one of the Mazda lead engineers. And they were looking for the perfect flame, right? So they were looking for the perfect flame that would give them, maximize their efficiency and also make the engine cleaner. So they actually looked towards CFD, computing resources. They expanded their computing resources. They realized that in order to do this, they really needed an accurate simulation, right? Because as we all know, garbage in, garbage out, right? If your simulation, if you give it bad conditions or if the solution isn't very accurate or whatever it might be, then you can't really trust where the CFD is taking you with the design. So they recognize we need an accurate simulation. We want to do this computer model based, okay? And then they did it first in the virtual world, and then they did it in the real world. So they designed the engine on the computer, and I'll just come out and say, because it is public, they did use Converge to do this. And they used Converge to design this engine computationally, and then they went and built it in the real world. Okay, so instead of making all these prototype vehicles or engines and testing them physically, which is the time-consuming, expensive process they had before, they're saying that really wouldn't have gotten nearly as fast to this engine as we did with CFD. So this is a big win for not only just for my company, but for Mazda and for CFD in general, for everybody that does CFD, right? This is yet another example of CFD really making a difference in the real world, and it affects things on a daily basis. Okay. So now I'm going to get into what is the future. So clearly the Skyactiv X engine and other engines as well have shown that there is more room to improve internal combustion engines. But we all know that electrification has been growing quite a bit over the last few years. We have the companies like Tesla that has really pushed the boundaries and pushed that forward. So what is the future, and why am I even talking about internal combustion engines? So some of you may be thinking that in the back of your head, like, why are we talking about this? You know, I read in the media every day that internal combustion engines are dead, or they're going away soon, or they're getting banned, right? So here's a headline that this is actually a little bit old now. They've actually moved the date up to 2035, and they're including hybrids now. But I know there's some consultation on this, and this could change, right? So, but at least at the time of this headline, Britain bans gasoline and diesel cars starting in 2040, right? So why am I even talking about internal combustion engines? Well, if you look at people's projections, and here's just a few different examples, and this is taken from a website called fuelfreedom.org, I believe is the URL, where you can go into that website and look at different institutions' projections, and also put in your own numbers, you know, your own thoughts, and have it create these graphs for you based on how you think things are going to evolve over time. But basically, what all the projections show, well, not all of them, but a lot of the reputable ones show that internal combustion engines will still be around for a long time, right? So if you look at the orange there, this is from 2015 to 2050 from three different. The Bloomberg and Goldman Sachs are projections. The IEA one on the far right isn't an actual projection, but a highly optimistic roadmap. And so if they could, you know, if they're being very optimistic about where we go with electrified and electric vehicles, this is where they think we could go by 2050. So the orange there are internal combustion engine vehicles, which includes gasoline, diesel, flex fuel, and also hybrids. And the hybrids in the orange there are full hybrids. So these aren't plug-in hybrids, but these are hybrids where the engine is actually charging the batteries, right? Toyota refers to these as self-charging. So that's what those are. So then in blue you have the EVs, and these are including battery or all electric vehicles, right? BEVs, and also plug-in hybrids. But again, even the plug-in hybrids still have internal combustion engines in them. And then the AFVS, the yellow, are alternative fuel vehicles, hydrogen, natural gas, and propane. So we don't really know what the future is going to bring, right? There are lots of different things. And if governments do start really banning things, that could change things a lot. But most projections show that IC engines will be around for quite a while. So what is the future? So when I'm saying that, but I don't believe that internal combustion engines are the only piece of the future. I think they're part of the future of propulsion. I think there is going to be more and more electrification, right? So I really believe that there is going to be more and more electrification. And that includes full battery electric cars, but also a lot of hybrid. There are a lot of different ways to do hybridization. There's mild hybrids, there's full hybrids, there's plug-in hybrids. There's electrified or electric cars with range extenders, which we'll talk about in a second. And then I think alternative fuels are going to be part of it too, where we're doing more and more with biofuels, possibly even e-fuels or, you know, carbon neutral fuels for IC engines. Okay, so the future, that's how I see the future. And so maybe some of you have seen this before, but a lot of people say the future is electric. I like to say the future is eclectic, which is a little bit of a play on words there. But what I mean by that is eclectic means kind of a mix of different things, right? And I think this idea of putting all of our eggs in one basket, I think is silly. And I think electrification and electric vehicles are a big part of the future, but we have to continue to also push internal combustion engines, both on the engine side and on the fuel side, because I don't think they're going away anytime soon. So we need to make sure they're as efficient and clean as possible. And that's where CFD can really help. So a little bit of a shameless promotion here. If you're interested in that kind of topic, you can visit eclectichighway.com. I have a podcast there that I do about once a week, and I have guests on there, and we talk about kind of the future of transportation. So check that out if you're interested. Okay, so now let's talk about what CFD features do we need to carry us into this eclectic future for propulsion systems, right? And I'm going to talk a little bit first about on the internal combustion engine side, but then I'm going to show later on in the presentation how a lot of these features that have helped us really move forward for internal combustion engines apply to e-mobility as well. And we can use these features to help us push forward electric motors and also batteries as well. So we'll hit on that in a little bit. But these are the features that I'm going to hit on. This isn't all inclusive, but These are the ones I felt like I wanted to talk about today. The first one is autonomous meshing, and I'll talk about what exactly I mean by that in a minute. Also, grid convergence, being able to assess how your solution changes as you refine the grid is a really critical component to being able to have, kind of faith in your CFD and understanding the errors that come with it. Scalability, of course, we always want to scale our codes more and more, and we want it to be able to run on more and more cores, and that is where everything is kind of headed. And so it's very important to have a code that is kind of built from the ground up to be able to handle scalability. And we actually just went through a major rewrite of our software. Well, I shouldn't say just, it's been a few years in the making, actually. And so our latest version, CONVERGE 3.0, is a pretty much, I don't want to say a complete rewrite, but pretty close to a complete rewrite of Converge. And so, because back when we first wrote this code, when it was just 3 of us writing this code, and most of the engine simulations, or a lot of simulations at the time, were done in serial. That's how old I am. Or if you were doing them in parallel, it was on a very few number of cores, right? And so we were writing our code thinking, oh, wouldn't it be great if we could run these simulations on 32 cores one day, right? So we were writing our code with that in mind. And you make different choices when you're thinking about 32 cores, 16 cores, even 64 cores, something down in that kind of area. You make different choices than if you're thinking about thousands and thousands of cores, right? So that's why we had to go through a code rewrite, because then we started seeing that no, thousands and thousands of cores really is where we're headed, and our code needs to be able to handle that. And so we went through this major rewrite, and that's Converge 3.0. So I'll talk a little bit more about that soon. And then of course, chemistry for chemically reacting flows, and also we'll see later, even with batteries for e-mobility, chemistry is important, and having a fast chemistry solver and an accurate chemistry solver is very important. And then of course, state-of-the-art physical models for whatever we're looking at, right? Whether it be sprays, fuel sprays for multi-phase flows, combustion, turbulence, and of course emissions, right? If we want to be able to make cleaner engines using CFD, we need to have confidence in the emissions calculations, and that can be pretty challenging. And I'm not going to go into the emissions too much today just because of time, but that can be pretty challenging. And there's been a lot of work there and a lot of progress in the last decade, I would say. And then again, we'll hit on e-mobility kind of toward the end of the talk. So what do I mean by autonomous meshing? So sort of the traditional CFD approach is, you import your geometry into your preprocessor. Somehow you mesh it up. Right now, depending on how complicated your geometry is, depending on if you have moving boundaries or not, kind of also depending on what you want to get out of your solution, that meshing can be anywhere from pretty automatic to painfully not automatic. And so this can be quite a bottleneck, right? So if you're filling your domain with tetrahedral cells, then maybe, and you don't have moving boundaries and things like that, maybe it's fairly straightforward. But for things more complicated, it tends to not be, right? Then you set up your case and then you solve. And for a lot of, at least what we were doing back in the day, and I know things have evolved, but back in the day, a lot of our time was spent meshing because we had complicated geometries with moving boundaries, and we had block structured mesh. They had to be block structured meshes. The code was very particular about how the mesh had to be, and you had to conform to that and things like that. So there'd be long meshing times. Excuse me, I'm just gonna take a drink here. And then we had, I took this phrase from a professor, and I probably should cite the professor on here, but that's not my phrase initially. Meshing by guessing is how he coined it, where you think you know where you need higher resolution, and oftentimes you do, depending on what the CFD problem is. Like if it's, if you may know, okay, I really need a lot of resolution near a wall, for example, or whatever it might be. So, but in a lot of cases, there is some meshing by guessing here. You could end up with skewed cells, and then grid convergence, sometimes it's so painful to make a mesh, you never even think about, what if I made a finer mesh? How would that change my answer? So our approach, this autonomous meshing approach, is, we've removed this meshing part. That's not 100% true, because we have added a feature in Converge 3.0 where if you want to, you can actually make like a boundary layer mesh or a prism layer mesh at your wall, at the walls, and then use our autonomous approach kind of within that, right? So if you want to, you can kind of bring back some of this meshing step here. If you want to have, you know, really fine cells near the wall and you want super control out of that, and you want to have, you know, high aspect ratio cells where, you know, you're really resolving normal to the wall, but tangent to the wall, you don't really care about the resolution. So we can do that easily with our approach, except you have to refine in all three directions. And so that can be, it's accurate, but it's maybe not as efficient. You may have to have more cells than you would otherwise need if you actually put in like a prism layer mesh. So with Converge 3.0, if you want to, as a user, you can introduce some of this back in if that's very important to you, but you certainly don't have to. And most of our applications, people aren't worried about this as much. And so, you know, we have removed this meshing step. So there is no meshing time. I mean, you have to set a couple of, you know, numbers in an input file or in the GUI, but there's no meshing time. And then we have adaptive mesh refinement. No more guessing as to where the mesh needs to be. You can use whatever variables are important for your simulation, whether it be velocity, temperature, species, and any combination of those to set up the AMR. So it will, you know, wherever you have high curvature in your flow, you know, that's where it will put in the AMR. And then orthogonal cells, which we know can be good for accuracy. And then it's very easy to perform grid convergence studies. All you're doing is changing, you know, a couple of integers in a file and you're on your way. So that's autonomous meshing. So here's an example that I like to show. And the reason why I show this example is because it's a very simple geometry, right? So you could easily mesh this geometry up in any preprocessor, any CFD code. It's just a channel with a little pipe at the bottom here, and you have flow coming up through the pipe into the channel, right? And you have a flow coming this way from left to right, which is kind of pushing. So it's like a jet and a crossflow, basically, right? So this would be very easy to mesh up in any CFD code. But if you look at where the adaptive mesh refinement is going, this is in Converge now, then that's putting the cells, you know, kind of where it thinks it needs it for the solution. If you had to predict where those cells would need to be, you'd have to make the mesh that fine kind of throughout the whole channel. So it's very expensive, right? So the other advantage you're getting with AMR and autonomous meshing is it's kind of putting the mesh where you need it, but it's not putting it where you don't need it, if that makes sense. And so you don't have to guess about where to put it ahead of time. It kind of learns from the flow where to put the mesh. Okay, grid convergence. This is another really important case or piece of the puzzle here. And if your answer is not grid converged, and if you don't know that it's grid converged, are errors due to the physical models? Say if you're running a spray simulation or a combustion simulation or even turbulence, are the errors due to the physical models or simply because you're under resolved, right? And so if you don't have any sort of sense of the grid convergence behavior of your problem, then you may not know that. And so this is just I put a little picture up here for reference. This is an injector. So this is a nozzle. So the needle moves up and down and the fuel is injected from left to right. And what we're looking at in this plot is the penetration of the liquid. So how far in this direction the liquid penetrates, basically. And we have experimental data for that. This is a pretty simple case, but it tells the story pretty well, right? So in the old days, what we would do is we would make a mesh for this. We'd probably be horribly under resolved, and then we would start tuning models to kind of try to get the penetration to line up with the circles here, the experimental data, right? So this is liquid penetration versus time. But now it's very easy to do these grid convergence studies. You know, so we went from 2 millimeters all the way down to about 30 microns for cell sizes. That's the finest cell in the domain from the AMR. Okay, and then we're able to show that at some point it's really hard to see the 0.25 millimeter plot here, which is unfortunate because that's about where we say it's converged. It changes a little bit after that, but you know, you have to kind of weigh the accuracy versus the runtime as well, right? So it's really not converged till about 0.125 millimeters, but that simulation is quite a bit more expensive than 1/4 millimeter because not only are you adding more cells, but now because of CFL requirements, your time step is also a lot smaller, right? So, you know, as a user, you can now decide, do I want to run 0.125 because I really feel like that's where it's converged, or am I okay giving up a little bit of accuracy because the runtime benefits are huge? Over here, this is a similar case, but imagine that now this fuel is evaporating and it starts combusting, right? So you get what's called a flame liftoff length, kind of at some point downstream. And you can also, very easily check the grid convergence of something like that, where here's the measurement for this case in red. And then as we refine the mesh, that's just a fixed value. I mean, the measurement doesn't care about the mesh size, so it's just a fixed value. And then as we refine the mesh, we get closer and closer to that result, but also the answer stops changing very much based on the mesh. And so again, we can be pretty confident that we have a good grid converged solution. So now if things don't match, now we know it might be in the models, right? Now we know maybe we should start tuning something. But in my opinion, you don't really want to start tuning stuff if you don't have to, until you know that the errors in your grid are kind of converged. Okay, and we use this kind of methodology, and this is work we did with Argon, Sandia, and also Caterpillar. And we use this to check grid convergence in an actual engine simulation too. This back here was a pretty simple kind of spray in a vessel kind of case, which is more of a fundamental case, but you put this in an actual engine and you start to see that, our results, which are in red here, match the gray results, which are the measured locations of the flame in the actual optical engine. We match it really well. We match the pressure, as we change start of injection timings. And I apologize, some of this terminology I'm using, you may not be that familiar with. I wish I had a whole day to talk to you guys about this stuff, but I'm trying to do this quickly here. But the moral of the story is we're able to get very accurate answers and do less and less modeling, right? So more and more, we're definitely not doing DNS here. I'm not going to claim we are. We're not even close to DNS in these calculations. But we're able to do less and less modeling because we've resolved more and more. Okay, so scalability. We already talked about this a little bit. We need fine grids and fast turnaround for CFD to make a real impact on designing turbulent combustion devices. You saw in the Mazda case, they realized they needed CFD to help them design this engine. They got more and more computing resources, and they needed software that could really scale. And so here's just a test case I want to show you. It's a pretty famous test case in the reacting CFD world. It's called Flame D. This is just showing velocity, temperature, mixture fraction, and CO. So it's reacting. It's an LES case. And we use this test case a lot to kind of show off our scaling because it has a lot of the features in it of that we really need in an actual engine simulation. And so here's just scalability curve, speed up versus number of cores. We did this in collaboration with Blue Waters, the Blue Waters machine down at NCSA in Illinois. And from 500 to 8,000 cores, we got very good scaling compared to the ideal curve. This had about 170 million cells. And we would expect scaling. We weren't able to run up to 80,000 cores. Hopefully we will in the future, but we expect scaling for this case, good scaling up to about 80,000 cores, which is very exciting for us for our latest version of the code. But now if we go back to more of a practical case, when we have customers run our code, they're not running 170 million cell cases, day in and day out. They do that once in a while, but their workhorse kind of calculations are more in the million cell. Maybe the peak cell count from AMR is something close, like in this case, to 1.25 million, 1.3 million. This is a standard gasoline engine case. It has all of the bells and whistles, spray, combustion, AMR, moving geometry are all part of the simulation. We're doing all the IO that we would normally do. So a lot of times when you see scalability plots, they turn off all the IO because it makes the scaling look better. Here we have everything. This is a normal case as we would normally run it in a production setting. And we ran this on our internal cluster. 28 core, 3.1 gigahertz Intel Skylake, single processor nodes. We do have InfiniBand interconnect and local storage. And so what does that look like? And so here again, we have an ideal and we have the Converge 3.0 speed up. And I realize we look super linear there at the early phases. Don't worry about that. I should have updated this plot. That was a little bit of a fluke. I need to update this plot. It's more right on the blue line. So I apologize for that, but the story is really the same. Once we get up to 450 cores, we're down to 1,600 cells per core, right? So there's not a lot of work being done on each core. And that's when you tend to get less and less scalability, right? But here we're still at 83% efficiency. And by the way, our previous version of the code, which we called CONVERGE 2.4, would have given you a result down here. So we've made significant improvements. Now, if we look at that in terms of this table, and we look at the number of cores, 56 through 896, and the speed up we get, but really let's focus on cycles per day, because as we do more and more advanced engine simulations, we've realized, and the industry has realized, that running one cycle, one engine cycle, that used to be good enough. It's no longer really good enough anymore, because now we're trying to find like really small changes in emissions and really subtle things throughout the simulation that you really need to include some of the cycle-to-cycle variation into it. So, on 56 cores, you may be able to run 1 to 2 cycles per day, right? But now if you have the cores available, if you have 450 cores available, you can run 12 cycles a day, and that's huge for our industry, because they used to have to wait, weeks or whatever to get multiple cycles, if they even thought about running multiple cycles at all. So this is a big deal for our industry. So we're very excited about this. Okay, now let's talk quick about combustion modeling. And I'm gonna go really quick here because I'm not going through these quite as fast as I thought. But for doing accurate engine simulations or gas turbine simulations or any sort of reacting flow, you need good chemistry. So this is just showing a small portion of a chemical mechanism. If you remember from your chemistry class, or maybe you do reacting flows now, we have all these individual reactions. You put all those together, you have your mechanism. And again, I'm just showing a very small portion of that here. So this can be very time consuming, right? And so we have lots of different ways we speed this up. One is a multi-zone chemistry solver, where we basically group similar cells together in the domain, whether they have a similar equivalence ratio, temperature. You can kind of set up what your definition of similar really means. And you can solve, instead of solving chemistry completely on every cell, you solve it in each of these zones, and then you feed that information back to every cell. And this can significantly speed up the chemistry calculation and still maintain very good accuracy. So here's an example of the runtime. So for this test case, we went from 31 hours down to, this is just the chemistry time. So not including the fluid dynamics time or anything like that. The chemistry time was 31 hours and went down to, less than an hour. So this is the type of speed up we can get with multi-zone, which is something we use kind of as our workhorse now in our chemistry solver. I'm gonna switch to this. This is a recent thing that we came up with, where how we solve the chemical mechanism is also very important, and we made huge gains recently. Our chemistry solver was already very fast, and I would argue one of the fastest, or maybe the fastest kind of in the industry. Other people may disagree with that, but from benchmarks I've seen, I think that's true. And now we've even made it even that much more faster, right? So for larger mechanisms now, we're getting speed ups in the latest version of Converge, anywhere from 2 to 3, maybe even 4 times of our old solver. So this is really exciting as well. Okay, I'm going to skip a little bit here because I'm trying to get to the end slides as well. This is some more work on Flame D that we looked at the scaling on before. And what I really want to show here is we also do a lot of, so validation is also very critical to, as you know, to CFD. And so we're constantly looking at, we put in new features, we put in new combustion models, we change how we do AMR, we put in a new LES model, for example. We're constantly benchmarking, these new models against not only engine data, something which is complicated, where you tend to have, emissions or big, global numbers, pressure traces and things like that, but also much more fundamental data. So this is, again, looking at, velocity, mixture fraction, temperature, species. So data we have at different locations throughout the flame. We're constantly coming back to this sort of data and kind of, testing our code against it to make sure that, we're just as accurate or even more accurate than we used to be. Our runtime didn't go down and things like that. So this is a really good test case we look at a lot. This is a bunch of experimental data we're comparing to, showing that our results look really good compared to it. So how will CFD help us? Well, I already talked a lot about internal combustion engines. There's a lot more I could say there, but just like it helped Mazda, we can use CFD to help design, more efficient and cleaner engines. I think the more and more we start looking at alternative fuels, biofuels, and things like that, even ammonia is being looked at as a fuel for like these large ship engines. Hydrogen is a really hot topic, no pun intended. But using CFD along with the chemistry really helps us kind of evaluate those concepts. And then of course, e-mobility. Real quick, range extenders for electric vehicles. There are people that feel like microturbine range extenders are the way to go. So they generate the electricity to charge the batteries. And they do have some advantages over piston engines, which is what we've been talking about. They have a lower power to weight ratio, lower emissions, no need for after treatment. Sometimes they have better fuel flexibility, and some people argue they have lower maintenance because they have fewer moving parts. So here's just a quick case we did that I'm allowed to show that's public of a microturbine range extender, and I just want to show kind of a CFD movie of that. You can see you have the moving boundaries, you can see you have the fuel injection coming in, and that fuel is going to evaporate, it's going to mix, and eventually up at the top here, we're going to spark it. Let's take a look at that. So there you can see we've sparked it, and you can see the flame. Okay, now let's look at e-mobility. I only have a few minutes left, but I do want to make sure I hit on this, as this is a big, this is a big part of the future of transportation, and we want to be able to, we want our CFO to be able to handle this as well as we, or even better than the engines, because our customers want to do both. They use our software for IC engines. They also want to use it for mobility because, as you saw earlier, the future is eclectic, and both of these things are going to be a big part of our future transportation. So first, how do we use CFD for e-mobility? Well, you can use it for cooling calculations, not only for the batteries, but also for the electric motors themselves. Okay, so I'll show some quick examples of that. And then thermal runaway is an issue. And this is something where we can bring our knowledge of combustion, right, into the e-mobility space, where you have thermal runaway, which can lead to battery combustion or explosions and things like that. So that's a safety concern where CFD can be helpful to try to improve. And we're really, because our software is well suited for 3D coupled flow, heat transfer chemistry, complex moving geometries, the autonomous meshing, we found, and we are finding, and our customers are starting to find, that we really do well in this area as well. So all of the key features that helped us in IC engines also help us here. So I'm not going to go through this, but I'm actually not a battery expert, but I'm pretending to be one right now. But some of you probably know more about this than I do. Just some lithium-ion battery basics. I'm going to blow through this quickly. We did this test case where we have an electrolyte battery pack, and we're looking at a cooling calculation and also thermal runaway. Okay, and again, this is just something that I'm allowed to show publicly, so that's why we're looking at this case right now. But there's some specs on the lithium-ion battery packs for electric bicycles, and we're going to use CFD to assess the cell temperatures under a very challenging operating condition, because that's when you might get thermal runaway, right? And then we performed event gas safety and thermal runaway analysis on that. This is just showing the geometry. This is the exterior geometry. Okay, and then if you look inside, you see the battery management system, or BMS. You see the spacer there, and then you see the individual cells. Right now, if we go even in further, you see the cell geometry, and these are 18650 lithium-ion cells. The 18 there means 18 millimeters in diameter for each one of those cylinders, and then the 65 is 65 millimeters high. So that gives you an idea of kind of the scale we're talking about here. This is just some of the setup things. I'm not going to go into gory detail here, but we assumed, you're riding your bike 11 miles per hour down the street, and here we looked at mesh convergence, right? And what we found is being able to assess mesh convergence is really vital to assessing how well you're doing on cooling, and also if you're prone to thermal runaway, right? So you can see here, as we refined the mesh, and then we also started using what we call inlaid meshes, which is that prism layer meshing that I told you we've added in our most recent version, right? So now you can have very, very fine cells normal to the wall and your boundaries, and then use kind of our Cartesian mesh kind of outside of that or inside of that, however you want to see it. And if we would have just used this coarse mesh, say this red case here, which converged down here, we would have missed the fact that we may get thermal runaway. And the reason for that is because thermal runaway tends to initiate around 80 C. And, it wasn't until we went to a fine solution here, which you can see in fine mesh around or near the boundaries here, where we were able to get an 86 C peak temperature. And then we could have missed that, right, if we wouldn't have done this mesh convergence study. Vent gas, I'm going to kind of blow through this so we have time for questions, but just trust me on this one. Here's a little animation where we're able to kind of simulate kind of a rupture at the top of the cell, and you have these hydrocarbons that kind of come out. But we also have to look at the effect of the thermal runaway of one cell on neighboring cells, because that's when this really gets scary, is if one cell heats up and then that affects the neighboring cells, and eventually all of this may go. Okay, so let's keep going here, vent gas. And here you can see a little animation of the vent gases coming out. That's what the isosurface is there on the bottom. Okay, now what happens if somehow that ignites? And that's what this animation is. So here at the bottom, see that isosurface, that orange isosurface is now temperature, and that's a flame. And we're resolving that with adaptive mesh refinement. So you get the thermal runaway, you get the vent gases coming out, and then somehow that can ignite. And it could be lots of different ways, but that ignites and that causes battery combustion. So that's a safety issue that we can look at with CFD that's very helpful to these manufacturers. Okay, electric motors, similar kind of thing. Different types of electric vehicles. Nissan Leaf has permanent magnet machines. Model S has induction machines. Model 3 switched reluctance machines. So there's different things we can do with CFD here, mainly cooling. And there are two different main types of cooling, air cooling, but liquid cooling is what's typically done for BEVs. You really need the liquid cooling to kind of get the cooling where you want it to be, using water jackets or winding sprays. Here's just a quick test case. Here's the geometry. And I'll just show some quick results here. You can see kind of the rotor and the stator there. And we did a cooling analysis here, and we got some really good results. And this is a motor that is being tested actually here at the University of Wisconsin. So we have access to a lot of the information here, and we can work with them to kind of do our validation. So real quick on the e-mobility side, I just want to kind of make it clear that autonomous mesh generation for battery pack geometries really does shorten the time to solution and allows for easy grid convergence studies, similar to internal combustion engines or any other application we look at. We have some strategies that I'm not going to go into here today for time, but we have something called supercycling for our conjugate heat transfer. We also have a fixed flow strategy, and this allows us to handle these disparate timescales, right? So you have, whenever you're dealing with solid and fluid, the timescales can be very, very different, right? And so different people handle that different ways, but we have a supercycling technique that allows us to do that. And then, of course, having fast detailed chemistry simulations not only helps us in engines, but it helps us when you're looking at thermal runaway in battery safety simulations. So that's proven to be very useful. And then, of course, you have this complex gap between the moving rotor and stator, and that can be hard to mesh and hard to handle when you're making a mesh, and that can easily be resolved for motor cooling and windage studies. And then when I talk to a group of CFD people, I always like to show this slide. This is my conclusion slide, and this is a quote from Robert McCormick. You may be familiar with it. There's a special room in purgatory reserved for CFDers, where they will be compelled to repeat by hand all the unnecessary computations that they have ever placed on a computer. So, of course, I want you to run as much CFD as you possibly can. That helps me out. That helps my business out. But we do need to be a little bit mindful about everything we run. You don't want to end up in that special room in purgatory. Okay, with that, I will conclude. So thank you very much.